we have the pleasure of having a talk from Professor Wahid Bajwa at the Rutgers University in New Jersey. Wahid graduated with his PhD from the University of Wisconsin and has recently had awards or I should say recognition like the IEEE Fellow position. So today he'll be telling us about interesting work of optimization in non-convex landscapes. So thank you, Wahid.
Okay, thank you so much, Laura, for hosting me. I appreciate everyone coming, despite it not the regular semester time. And this is sort of like a talk where I'm trying to compress a lot of different ideas and trying to convey the gist of it. And if you have any questions, I would like it to be more interactive rather than me trying to go through all the slides. So let me first get started by mentioning the key person who actually did most of the work, my former PhD student, Rishabh Dixit, and my collaborator, Mert Gurbuz Balaban. And this talk is kind of compressing, as I said, 3 papers. So we'll reference those, but if you are interested, you can go and read up. 2 are published, 1 is in revision, but available on archive. So what I want to do is start with first motivating the problem, because the way the problem has been set up is not very typical in optimization literature. So I want to first do that. Then I'll talk about just regular gradient descent. And after that, I'll talk about accelerated methods. And then we'll try to conclude with that. So let me get started with the main motivational thing. The problem we are trying to study is classical optimization. We have a smooth function f of x, unconstrained problem, no constraints that are being attached to it. And since we are interested in solving large-scale versions of these problems, we are only going to work with first-order settings. So what we have is that we are given the gradient information, and we want to optimize that. And of course, this is something that we have been studying for decades and decades. We used to study a lot of this 2 decades ago within the convex landscape. So convex optimization problem was really big in a couple of decades ago. But then we realized that most of the interesting problems are non-convex, and the non-convex problems have their very complex geometry. So we need to understand that complex geometry of the non-convex problems well, and that is what the focus of this talk is. It is primarily about non-convex problems. In a non-convex problem, of course, we have for a first-order method, which uses gradient information, we have 3 kinds of stationary points. We have global minima, local minima, and we have saddle points. All of these points have the gradient 0, which means that if you are using any first-order method, that's a fixed point of your equation. And so you don't, once you reach there, you get stuck there, right? You can't update yourself. So while this is true, people heuristically knew for a while that for some reason, when you run gradient descent, even though a saddle point where the gradient is 0 is a fixed point of your gradient descent dynamics, you almost never go there. But mathematically, and there have been some earlier works as early as 1970s that tried to explain this phenomenon. I'll reference that paper later. But a big flurry of this activity started around like about 7 or 8 years ago, when a paper came out, a very simple paper based upon dynamical systems analysis using stable center manifold theorem for people who are familiar with that, which showed that gradient descent almost surely does not converge to a saddle point, okay? And that kind of unleashed a lot of interest in that area. But there are a lot of things that are not answered from works like that. One thing is, okay, it doesn't converge, but you could still spend an infinite amount of time near there before you escape. So how long does it take you to stay there, or how quickly can you leave that region, right? That wasn't very satisfactorily addressed. In fact, people came up with pathological examples showing that, yeah, indeed, you could just be spending the time at their infinite amount of time. Secondly, the question is, okay, let's move on from vanilla gradient descent. Let's talk about accelerated methods like Nesterov's accelerated method, momentum-based methods. And for those, what do we know about those things, right? And so some of the work in that earlier work existed was heavy ball method. I'll discuss that later. But even there, we didn't fully understand. One of the questions for accelerated was also that, momentum, we know plays a huge role in how do you converge to local minima. For example, heavy ball overshoots. Nesterov's method, if you use the right momentum, it gives you the optimal rate, right? Now, is there a trade-off between, for example, escaping saddle, leaving the saddle region quickly versus getting to the local minima, right? So these are a bunch of questions that were never addressed satisfactorily. And the reason for that is because the machinery that we have to analyze optimization methods doesn't allow a good characterization of these questions, because typically when we are doing non-convex optimization, we are trying to say, well, does my gradient norm goes to zero, right? That's the typical question we ask about, and that doesn't allow. Or the other thing is, if you are doing even, you go after descent lemma and you try to do telescoping sum, it doesn't really give you a machinery to analyze the questions we want to ask. So part of this talk is setting up that machinery, giving you some, let's say, terminology or setting up the basic problem that can lead to addressing the kind of questions I want to address here. Okay, so what are the kind of questions we want to address? First is, given what is known, accelerated methods. Do accelerated methods avoid heavy ball in general settings? The work before that showed that heavy ball does escape saddles, but that work only focused on quadratic problems. So for quadratic non-convex functions, they showed that. Can we show it for general accelerated methods on general non-convex functions? But even going back to just non-accelerated methods, just gradient descent, how many iterations does the gradient descent method spend within a saddle neighborhood? And how quickly can it escape? Can we set up some conditions that will allow you to escape it faster if you have those necessary or sufficient conditions known, right? So we want to set up an algorithm that doesn't require a lot of added complexity. People have set up methods that do, for example, use Hessian information, but we don't want to have a very complex method. And then the last question is that what is the role of momentum in accelerated methods when it comes to the trade-off between escaping saddle points and converging? So these are sort of like the questions we want to address. And the talk is going to be divided into two pieces. One is I'm going to focus only on gradient descent first, because from the dynamical systems perspective, it's very simple. You don't have complex dynamics, and you don't have your trajectories don't spiral because of that. So it's easier to analyze. We derive sharp exit time conditions. We define the notion of exit time, provide some basic results. I'm going to skip over a lot of mathematical details, focus on some of the key ideas. And then based upon those conditions, set up a simple variant of gradient descent, which checks if you are in a saddle neighborhood to make sure that you can escape exponentially fast. Yes, please.
Do you also consider the perturbed gradient descent?
Yeah, I'll talk about that. Yeah, that's a very good question. And effectively, perturbed gradient descent, we will show, for example, heuristically why that might work based upon the conditions we'll derive, okay? So that will be sort of like a one subroutine in our work. And then we'll move to accelerated methods. Accelerated methods are much difficult to analyze in this setting, because when you view, first of all, whether you view them as dynamical systems in N, where N is your ambient dimension, or 2N, the trajectories can basically spiral around the saddle neighborhood. The other issue is that momentum-based accelerated methods in the Euclidean distance, they are not monotonic, right? So if you, for example, do Nesterov, whereas gradient descent is going to go down objective function, if you look at Euclidean distance, it doesn't monotonically do. There is a Lyapunov function under which it is monotonic, but finding out the right one for our analysis is one of the major challenges that we'll do. And we'll try to characterize basically the trade-off between escape and convergence, and also look at the almost sure avoidance for general non-convex problems. So that's sort of the thing that we are going to cover. But before I do that, I do want to provide some historical context also and some prior work. So there are a lot of, this question, of course, it didn't come out of thin air. People have been studying that. One of the earlier works that we found, there was Gelfand and Mitter's paper that I'll show later, Kiefer's work in 1981. A lot of initial work focused on basically approximating these problems through continuous time models of first order methods. So basically effectively thinking of your first order methods as Euler discretizations of your ODE problems, right? And there you can show that, you can just use classical continuous time dynamical system theory to show that, yeah, this wouldn't happen. The challenge is that, of course, to make the approximation work, you have to take the step size in your gradient descent method to 0. So effectively, yes, as you take the step size to 0, it happens, but none of us want to run gradient descent or any optimization method with a step size which is infinitesimally small. And if it's not infinitesimally small, then do these statements still hold, right? So a lot of these works are great. They are ODE-based interpretations, but from the question we want to really address, they are like a first order answer to the question, but not really the answer that we are interested in. There is a whole host of other works that exist which talks about why gradient descent, for example, would not converge to the saddle point or will avoid the saddle point. People use different terminology. Sometimes they say it wouldn't converge to a spurious local minima, right? These problems are based upon specific problem structures. So they are not general statements about non-convex. They are like, okay, if I'm doing, for example, phase retrieval, it has very particular structure, and that structure, I can do the analysis, but they are not generalizable. And there you can say, oh, it doesn't converge it or to the saddle. The general convergence rates are X, Y, Z. There is as I said, the interest started in this area again from this Jason Lee's paper in 2017. These are all sort of almost sure convergence type of results, asymptotic convergence results, and the two of the major results are this for gradient descent and O'Neill and Steve Wright's paper on basically heavy ball method, and in general, primarily for the or exclusively for the case of quadratics. So it doesn't apply to non-quadratic, non-convex functions. I was referring to earlier, one of the other works was this Gelfand and Mitter's work in 1991, based upon the Langevin dynamics-based stochastic flow models. So that's this. Then people also got interested in, okay, what can you say about higher order methods? So there have been works, this Anand Kumar and Gay's paper looks at, for example, you have higher order methods go beyond that. Then you have other works that look at Newton type of methods, the Hessian type of methods. Of course, we are not interested in that because we want to stay with just first order methods for simplicity. Once people realize there is almost sure thing, this is just one piece of the puzzle. I'll talk about more perturbed things, but one of the things people said was, well, if we just add some noise to our gradient step, right, it should help you, and people were able to prove things that they called it perturbed gradient descent. It effectively just, effectively add noise to your gradient itself. It's not really, but you can map it to SGD setup also, and that's why like people say, okay, now SGD wouldn't have this property either. But again, it doesn't really answer the questions we are asking, which is how much time does it spend there? How quickly can it escape? What are the conditions, right? Should we keep on adding noise all the time? And that's the question. The analysis will then, you can connect it to this and say, you don't have to add noise all the time. At this condition, when you don't have that condition satisfied, that's when you can add the noise. Okay. And then people have looked at some momentum and various acceleration-based methods, but they are very much in the same vein as I talked about earlier, where they are talking about momentum-based escapes, but they don't ask the question about exact escape, and they are not asking the question about what is the interplay between escape and convergence. Even a question as simple, and we don't have full answer to that, right? But even a question as simple as, so we know that, for example, Nesterov's method will converge faster than gradient descent, right? What about escape? Does it escape faster also? Like, because it's all about convergence. You are adding momentum to converge. Like, now should it escape? So even as simple a question about comparison between gradient descent versus this, we don't fully understand, right? And so those are what we are interested in. And so we'll do, as I said, we'll move to the gradient descent question, but I want to make sure that everyone understands the setting of the problem before I go there. If I have any questions, otherwise I'll go to the next one.
Yes, out of curiosity, what happens to methods like linear conjugate gradient or quasi-induced methods?
Yeah, so excellent question. So conjugate methods, I mean, of course, they are type of accelerated methods, this setting. So what the accelerated methods we are focused on are momentum based. So our analysis does not apply at all. And to the best of my knowledge, I have not looked at conjugate gradient, any results involving conjugate gradient. The quasi-Newton things, you could argue that it could, some of this, so this is a group that has worked on Aryan Mokhtari's group on basically Newton and quasi-Newton type things. And you could argue that some of that could apply to that. But again, the statements are more along the lines of it doesn't converge almost surely kind of thing. Those are the kind of statements that are made. So to the best of our knowledge, that the problem, once you see that, right? And so far I had kept it very generic. When I pose the exact problem, you would see no one has looked at it from that perspective because we didn't even have the right, you can say taxonomy for talking about those questions. And hopefully, by talking this, that can lead the door, open the door to future work in that direction. Okay, so let's get started. Gradient descent, as I said, we have a smooth non-convex function f of x, unconstrained problem. And n is the dimension. We only have access to the gradient. And we are interested in running this gradient descent update with a constant step size alpha, which we are not going to let go to 0. And as I said earlier, unlike classical non-convex analysis, which focuses on, for example, the gradient norms or the function values, we really want to understand how the iterates, how xk itself spend time in the neighborhood of the saddle point. Because if you want to understand how quickly it escapes, we have to really get a handle on that. And that's why we really have to think of it as a dynamical system where this is the state of your system, xk, and where it is, where the trajectory is in that neighborhood. So let's put the formally look at the assumptions that we are making. The problem we are going to ask is for the case of a Morse function. A Morse function fundamentally is a one that only has what's called strict saddle points. So saddles come in different shapes, right? You have this, which is called the monkey saddle, which is a non-strict saddle. So a non-strict saddle is one where the Hessian of the function does not have a negative curvature. It doesn't have a negative eigenvalue, okay? So that's the non-strict saddle. We are not interested in that. This is a thing where it has a negative eigenvalue, positive eigenvalue. This is a strict saddle. We are also interested in only strict saddles. The theory that we are developing can be mapped to a degenerate strict saddle. So what's degenerate strict saddle? That it has the negative curvature direction, but it has a 0 eigenvalue. So it has a lot of flatness around your saddle, okay? So this is what we call a degenerate strict saddle. We are not interested in that either. As I said, some of the theory can be mapped there. So the main thing we are looking at is non-convex problems, and we are interested in a strict saddle where your Hessian has negative eigenvalues and no, your Hessian is not basically rank deficient. It doesn't have a 0 eigenvalue. Yes, please.
Does this property need to hold everywhere globally?
Well, for the saddle we are analyzing, right? So because we are only interested in that saddle part. Now, if you want to talk about global convergence, you can always talk about the worst case that somehow you were so unlucky that you visited every saddle, then you would have to do that, okay? So the other thing that we have some classical assumptions, but one of the things is we need, again, the saddle neighborhood that we are analyzing, we want the function to be analytic there. C infinity even is not enough because of the machinery we are going to use. We need it to be analytic. The other assumptions are, okay, we want it smooth, so we have L Lipschitz gradients. So L will always represent my Lipschitz gradient constant. But I want my Hessians also to be Lipschitz, okay? And M will be that, and the reason for that is because I want to basically approximate the Hessian at the saddle at other points, because that is what will allow me to understand the trajectory better. So I want the Hessian to be smooth also, okay? And the other thing is, as I said, we have a strict saddle whose Hessian is not rank deficient, but I also want the minimum absolute value of that to be bounded away from 0. So beta is how much I am away. The last condition is kind of simpler because we write vectors in terms of the eigenbasis of my Hessian, and if my I can have basically repeated eigenvalues, but this delta is that it appears in the analysis, but it's not that important. So fundamentally, we have a locally analytic function with strict saddles, Lipschitz, my gradients are smooth, my Hessians are smooth. And I'm bounded away, my Hessian is bounded away from the conditioning of that, the smallest eigenvalue, it's bounded away from 0. Okay. So what's the question we are asking? Let's assume that you are analyzing a saddle point X star, and you are dealing with gradient descent, and somehow you arrived at the boundary of that, right? How you arrived at the boundary, we don't care because the past is immaterial for us in that case. So without loss of generality, you can say you even initialized at the boundary. Epsilon is the radius of the boundary that you are looking at, okay? And so this is xk minus x star will always be working with this radial vector uk, right? This is sort of like a surrogate for what xk is, because x star is fixed. In traditional gradient descent, of course, the question we ask is, you assume x star to be a local minima, and you say how long it will take you to get to this point, right? Here we are saying we are sitting at the boundary, and you are going to start getting pulled towards the saddle because it has attractive dynamics, right? But eventually we want to leave. We know that we would leave under some conditions. We don't fully understand them. And so we call that the exit time, which is the time, the minimum K. Once you enter this ball, the minimum K it takes you to have the radius of this become greater than epsilon again, right? So that is the definition of what we call exit time, okay? So very precise definition, and in a very similar way to how we go after. So in convergence, our holy grail, for example, a strongly convex function is, can we get linear convergence, right? It's an optimization term. If for linear convergence means you go exponentially fast towards within the epsilon neighborhood. Here we are asking, can we leave this ball exponentially fast? So we borrow a similar terminology. It's a slight abuse, but it's kind of similar that now, linear convergence, every time you are reducing it by a constant factor. Here we are saying, let's assume that you are getting away from it by a constant factor. So we say we want to escape in linear time, which means the time it takes you is only logarithmic in epsilon inverse, okay? So if you are there, it takes you only log of epsilon inverse to leave this ball. We call this linear escape time or linear exit time. Yes, please.
Definition of the exit. Why are we using infimum instead of the largest K?
Because this is the first time you leave the ball.
would we also be interested in the longest amount of time during which we can be?
Right, so the longest amount of time could be, we already know there are pathological examples that you could just keep on spending time there within that saddle neighborhood, and it could actually converge to infinity, right? So it's sort of like we don't want to spend enough time there. So what's the first time? Now, the question you could ask is it possible for you to leave this and come back, right? That we address also, that actually as long as the gradients in this region satisfy are higher than a certain threshold, you would never return back to your saddle neighborhood. So that's why it's the infimum, the first time you leave. Okay.
Along those lines, though, like, so a smaller region around, I think it would be a higher chance of coming back. But also it feels like you should be able to leave faster, right? But if epsilon gets small here, you're saying it takes longer to escape.
Right. So somehow, yeah, because if you get closer right now, think of it as, you are really pulling toward, like a magnet, you are pulling the trajectory. So if you were really close, now actually it's going to get harder to leave because the pull is too fast, right? Yeah, so it's kind of like, the mappings don't fully align with our traditional thinking of the convergence part. Yeah. Yes, please.
This often depends on initial condition. I was imagine if you start in this K X isn't already, you are getting pushed away immediately. So
Right. So we'll show the result that the analysis we are going to do is, for example, right? The analysis can't hold if epsilon was like a million, right? You have to because we are going to be doing approximations in terms of the gradient or Hessian in this region. So if my epsilon was too big, the whole analysis breaks apart. So this epsilon is a function of basically the beta that we have talked about and your M and L. I'll show you that later. But yeah, it can't be too large of a ball that we are looking at. Yes, please.
same lines, is that like, it seems like, yeah, it seems like the trajectory you're going to take, maybe the exit time itself is going to depend on your initialization point. So
Yes.
like making some assumption about like.
Right. So that is what we want to derive, right? That is what we want to derive. So the question is, right? The question is, under what conditions this would happen, right? I can write it down, but I don't actually know. First of all, I don't even know it would happen. So we'll first derive necessary conditions, okay? And this is what we want to ask, that, before this, it wasn't even clear that can you actually escape this fast? Or maybe you can't, right? Like, for example, only strongly convex functions give you linear convergence. So maybe in this case, it won't happen. So that's what we want to derive. Absolutely. Okay. And if we derive the condition, then we can go after an algorithm. So to do this, actually, we just take a very simple breakdown of your manifold around the strict saddle. So we look at the Hessian at your saddle point, and the Hessian, of course, it has eigen decomposition, and what it has is it has two subspaces. So first of all, it doesn't have any center subspace because my lambda equal to 0 is not an option. So I have my lambda is greater than 0, my eigenvalue is greater than 0, and they are what are called stable subspace. The eigenvectors that span this are the subspace which are pulling your trajectories towards, they are the attractors from the dynamical system language, right? They are the attractors for your trajectories. And then for lambda I less than 0, which is this direction, right? They are your repulsive dynamics. They are what's called the unstable subspace. And really the name of the game is that if you, for example, if you landed, going back to your initial condition thing, if you landed exactly on your stable subspace, you are now picking no part of the repulsion. So you are going to get sucked into the saddle point, right? And the whole idea is that, well, so we know if you align, and that's where the almost sure part comes, to that to actually, the only way you'll get sucked into the stable subspace or into the saddle is if you align perfectly with the stable subspace. And so if you randomly initialize, almost surely you are not going to align with that. And like, that's sort of like a 1 minute proof of why it doesn't converge, right? But the question is, how much misalignment do you need to be able to do fast convergence? So to do that, we really need to understand the breakdown. We need to represent UK in terms of its stable and unstable subspaces. But UK is sitting over here, so and I don't know all the description about the Hessian, so that's the challenge. But what I need to do is take my initial projection. This is the role of the initial condition, right? So my initial vector is sitting at epsilon distance, so it has epsilon, that's the epsilon, and I write it down in terms of my stable and unstable subspace. And the whole game is, what is the contribution of this? Because this is what's going to push me away from the saddle neighborhood, right? If this contribution, if this projection, this is the projection of your initial vector onto your unstable subspace. If this projection is 0, you have no hope. But the question is to get linear escape, how big this projection needs to be. Okay? So the whole thing we care about is we can answer the question in terms of actually the angle that your U0 makes with the unstable subspace. And that angle is given by simply the coefficients when I expand it in terms of the unstable subspace, the coefficients associated with the eigenvectors of my unstable subspace square, which is simply the cosine square of the angle. So if this, as I said earlier, if this cosine square of phi is 0, you are perfectly orthogonal to your unstable subspace. You are not going to escape. But how small can this angle be? Do I need it to be pi by 4 to do linear escape? Do I need it to be pi by 3, pi by 6, right? And we have a necessary condition. First thing is, there is no way you can escape linearly fast if this angle is smaller, or cosine square theta of this angle is smaller than this quantity. The step size is 1 over L, so we are using the best step size, right? For descent. So as long as the cosine square of the angle is bigger than log epsilon inverse square times epsilon, right? So the smaller the radius is, for example, right, you can be actually more aligned, and that is okay. But if you are any closer, the sliver of the subset, if I just look at 2D, the sliver of this region that you need to land in to not do linear escape is extremely small. Most of the angles are totally fine. You can land anywhere as long as, well, this is my stable one and this is unstable now, right? As long as I don't land in this tiny region in my initialization, I can escape. I might be able to, this is necessary condition, I might be able to escape. But if I land in this region, it's end of story. There is no way I can do that, right? But going back to, for example, the perturbed one, since this region is so small, if I landed here, I can just add a little bit of noise and it will push me out of this region. Okay? So that's sort of like a more version of how you do. And the conditions are, as I said, you can derive conditions on epsilon, the radius. This holds if epsilon is less than beta over 2 beta over m. Okay? Or you can view it differently. M is the Hessian Lipschitz constant. So the M is the Hessian, beta is your how much you are away from your eigenvalues are away from 0. Okay? Yes.
There's for the when your angle is 0, you are perfectly aligned with the US. So that means you can perfectly escape, right? So the phi needs to be pi over 2.
Right, so if you cosine square, if this is your this is the angle you make, so if your cosine square theta is 0, cosine square phi is 0, you are making a pi by 2 angle with the unstable subspace, which means that if you're orthogonal to the unstable subspace, you are not going to escape. That's what this means, right? So if this quantity is too small, which means you are getting closer and closer to pi by 2,
Yeah.
with the unstable subspace, you cannot escape.
Yeah.
Okay. So, okay. So the way this works is, and then I'll give you the sufficient condition. The key idea here is that we express the gradient in terms of the Hessian. So we do a first order approximation, but there is an error term, and the whole deal is getting control of, we do a gradient approximation, we do a curvature approximation at our xk point in terms of the Hessian at the saddle. In both of those cases, I have error terms, okay? If I want to say this, I have to have a good control on these error terms. And local analyticity allows me to get a good handle on the error terms for gradient approximation. And then what we do is we really try to express this Hessian at any point as a function of the Hessian at saddle plus this error term using matrix perturbation theory. So we are able to represent, for example, the eigenstructure of the Hessian at any point within that neighborhood using matrix perturbation theory. And when epsilon is small enough, that approximation error can be controlled very well. So that's sort of like the upshot. And now we can do this to give you sufficient condition also. So the sufficient condition is that as long as the angles, the cosine square of the angle is bigger than 1 over log epsilon inverse, right? And you can do the plots of the two. There is a small gap in the beginning for epsilon small, right? So there is a gap between the sufficient and the necessary condition, but it's not that huge of a gap. Effectively, it is still saying the same thing, that as long as you are not too close to the stable subspace, or the angle between the unstable subspace and your initialization is not too close to being pi by 2, you can escape in linear time. This is a sufficient condition. You are guaranteed escape in linear time in that case. Okay. Just to give you a very visual guide to how this proof is done. So imagine this is my strict saddle, this is my stable subspace, and this is my unstable subspace. If I did, for example, an ODE-based analysis, I get this hyperbolic flow curve, but this is only for alpha going to 0. I can't afford that. The challenge over here is, this is where I have landed. So part of the thing is, what we are saying is, if you are in this region, if you landed between this and this, you have no hope. But if you landed away from this region, now anywhere over here, right, or over here or over there, right, then you can escape fast. To do that, the fundamental challenge is that if I do analysis using all the eigenvalues, it will be very ugly and we won't be able to get a control on that. So the trajectory is going to be to a function of all the eigenvalues and all the eigenvectors, right? So it's going to be, so what we do is we do a worst case analysis. We parameterize, we say we have a trajectory, each trajectory corresponding to the eigenvalues of the Hessian, okay? So we have an infinite number, so we have an infinite set of trajectories, and each one of them is going to be different trajectory. What we do is the worst case analysis, we come up with this worst case trajectory, which takes the infimum of all possible trajectories at each point. And our result is about the infimum trajectory exponentially fast, so everyone else would have to do pretty fast, okay? But the fundamental conclusion stays that as long as you are not too close, you are good. Now, how do we actually do that? What if the condition is not satisfied? You can't really check the condition, right? You can't really say, oh, if I'm too close, you want to build a method. It turns out actually you can do a very simple approximation using difference of Hessian. It's sort of like the secant condition in quasi-Newton, not exactly, but we can give you an exact condition where you compute these two quantities. This is the difference of the two iterations, and this is you are projecting them onto their gradients. So this is kind of giving you an approximation in terms of the Hessian at the strict saddle. You subtract the two quantities. If this difference is large enough, you are guaranteed that you are not too much aligned with the stable subspace. Okay, and if if this difference is not large enough, it has two meanings. Either you are at local minimum, right? So you have no unstable subspace. Your Hessian doesn't have you are at a perfect local minima, or that you are not satisfying the angle condition. And if you are at a local minima, life is good. But if you are not satisfying, so we provide this algorithm, we call it CCRGD, which is simply do gradient descent. Once your gradient norm becomes too small, now you don't know whether you are at a local minima or at a Hessian, at a strict saddle. So you simply check the condition that I talked about, V1 minus V2, right? If that quantity is large enough, you keep going because you will just escape. If that quantity is not large enough, you can do one of two things. One is you can do something like perturb gradient descent, add some noise. It's going to throw you off that sliver of the region. Or you can do a Hessian calculation. What you can do is simply find that direction. Now do this kind of a step. Find a direction which is maximally aligned with the negative curvature. So effectively solve a constrained eigenvalue problem where you are looking at alignment with the negative negative eigenvalues eigenvector. And if you can't find this, if there is no negative, if the value is if the value is non-negative, then means that there is no negative curvature. Since we assume strict saddle, so that means you are at a local minimum. Yes.
It's a little bit unclear to me where does the assumption that you cannot have, at least based on the analysis you have, the assumption that you cannot have zero eigenvalue for the Hessian, where does that come into play? Because based on my understanding, you need to look at the projection onto unstable space and stable space. And zero, you can think of this as like a part of the stable. You're not gonna.
Right. So the as I said, that you can extend this analysis to degenerate strict saddle. Okay. So strict saddle you cannot avoid. Okay. You have to do strict saddle.
Yes.
But you can extend it to at the expense of just more tedious maths. That's where the assumption is. Okay. You can. It's not that it doesn't work. The math just is unnecessarily complicated without really adding too much. In that case, as I said, you would, and in fact, when we do the accelerated, we have to deal with it, and we do deal with the center manifold in that case. But you are absolutely right. It's not detrimental. It's just that it adds more constraints because now I have now I have basically associated with that zero eigenvalue. Since I'm doing expansion in terms of all the eigenvectors, right? Now I have to worry about if there are multiple of those, then I have to, figure out the vectors that are going to span that space and all that. So it just makes things unnecessarily tedious. And in our matrix perturbation theory, it makes it very, very messy. Doesn't mean it doesn't work.
A lot of these problems, especially like null setting, they tend to be like over parameterized, which means that your Hessian almost, like, even in the solution that you want to recover.
Right.
Tends to be lower.
Yes.
Which means that you have a lot of zeros.
Yeah, no, absolutely. And so it's not that, it's not that it doesn't work. It's just, it doesn't add too much value to the analysis. That's the reason we avoid it. Okay. I want to quickly, well, we have convergence results for CCRGD, but in the interest of time, they can be improved. It's with a lot of caveats, how many strict saddles you have in the neighborhood and things like that. Here we do use the fact that you don't come back to the same saddle neighborhood if you have exited it once under certain conditions. But let me just quickly provide you some result, and then we'll move to a momentum-based method. So the function we work with is, this is a Rastrigian-like function. It's modified because it doesn't have the quadratic term, and we change the VI. We construct it so that 0 is a strict saddle. And what we do is we initialize in a radius around epsilon 0.00001. And we have, this is a 10-dimensional problem. If you look at over here, this is the eigenvalues of the Hessian at where we are looking at, okay? So when at k equal to 0, you can see that there is one negative eigenvalue. And then we run CCRGD, which is our method, which versus gradient descent by itself, okay? We have basically initialized at a point where things are really bad, right? So gradient descent, even though it is supposed to escape, and it does escape, so there are three. This is the curve for distance from initialization. It is really stays close, and this is the gradient norm, right? You are in the blue is gradient descent. Your gradient norm is slowly increasing, which means it is going away from saddle, but it is very slowly, okay? But, and if you come over here, by the time you finish, the red is the gradient descent, and you see it is still in the saddle neighborhood. It is still has curvature, negative curvature. It is still moving away. This is CCRGD. What happens is that over here, it realizes that it is too close to the saddle, to the stable subspace. It does that perturbation and it exits at this point. And so what you see over here is it is exiting and it goes all the way, which means that it moved far away, and now it's going back, gradient is going back to 0. Why it's going back to 0? Because it has now gotten pulled into a local minima. And how do I know that it eventually got to a local minima? Because if you look at the eigenvalues of the Hessian, they are all positive, right? So you can compare that, first of all, it is not just hypothetical that, oh, you didn't need all this theory, gradient descent would have escaped fast anyways, right? This is just a proof that that's not the case. It is actually pulling very slowly. Even after 100 iterations, gradient descent is not out of the woods. Whereas by doing the right perturbation, we got out of it very quickly. Yes?
Is this with random initialization?
No, we initialized it very strategically, right?
But so gradient descent, the paper that you were referring to, it requires random initialization for that to converge to a second order stationary point almost shortly.
No. So by the point over here is random initialization is not the focus over here. The point I'm trying to make is that we know that gradient descent, before this work, we knew that gradient descent does not converge to the saddle point. But the question we were asking was, what if it is slow escape? And our method gives you fast escape because we have this condition. So what is happening is we initialized it in the region where it's going to be slow escape. But CCRGD, it checked that condition based upon the theory and quickly realized that it is aligned too much with the stable subspace. So it moved you from there, and then you quickly escaped faster and came back to local minima. Yes.
Sorry, one. Okay. I have a two-part question. So first, if we have a landscape for which the concern is not to escape from saddle points, but we have many local minimizers, and I'd like to explore them
Yes.
as much as possible. So I increase exploration. Like with the techniques developed here, be used instead of escaping saddle points and never return, or
Mhm.
like a push from like the skeleton returning.
Yeah.
Can we use it to explore the landscape for more local?
Right. So it opens up a lot of questions. And again, we are just building the machinery because as we discussed, tools like this haven't existed, right? Like the other thing where people say, well, if you go to a flatter local minima in empirical risk landscape, you will generalize better, right? I mean, all those questions come into play. How can we get closer to those kinds of things? And people have, most of their analysis has been based upon, well, if we have stochasticity, we are going to just jump over things and get to a local. So these can perhaps help us address some of those. But yeah, the question you're asking is great. I don't have an answer for that. Yeah.
So, what about if, like, what are the challenges if we have, say, like the simplest set of constraints, like box constraints,
Mhm.
a projection to like 0, 1, or
Yeah, so constraint optimization, it's sort of like the similar thing that, now, if, for example, in your neighborhood, some part of the neighborhood doesn't satisfy the constraint, right? It's sort of like the same. You're doing constraint optimization and your solution lies within the constraint set, great. Otherwise, you are gonna be optimal will be at the boundary, right? So similar kind of things, right? And it's not really clear. Again, we have not looked at it there at all. So. Laura, you had a question or? Yes, please.
So, that test that you have in terms of V1 minus V2.
Yes.
Is only applicable to gradient descent, or you can apply that to other methods using gradient descent?
No, this comes out of basically the analysis. Again, I didn't go into the details, but it comes out from the fact that where did it go? That we use it as a proxy for our projection, right? And how much projection you need to escape, that comes out from the analysis, the sufficient condition. So we map it to there to come up with we have a precise quantity that you need, right? So other methods, the quantity will be different. You could use it, right? But I mean, at the end of the day, the game is about not too much alignment with the stable subspace, but how much alignment you need and how does that map to something like this. Those, if you want to give precise constants and everything, that's going to depend upon the method you are dealing with. Yeah.
In general, being away from the stable subspace is better. You can use that quantity to know.
Yeah. For gradient descent, yeah, you can you like we have a very precise. And again, if you don't, right, then the perturbed one is another option. If you believe that the region which is bad is very small, then just add some noise and hopefully with high probability. There's a high probability aspect there. With high probability, you will land in a good region. So, okay. We have another 18-dimensional thing, similar case happens, but in the interest of time, because I think I'm pretty behind, okay, so I'll try to wrap up then within 10 or at least give the gist, right? The questions so that's great, but now if we move to the momentum-based acceleration, we have a lot of questions. We don't, for example, know that, what kind of momentum to use for faster escape, right? And do we escape better than gradient descent, for example, the conditions? Is there, even as I said, for general non-convex functions, we don't know if we have almost sure convergence. So what we do is we actually analyze this method, which is a generalization. I'll show you how that breaks down to our classical Nesterov accelerated method, for example. We analyze this expression. So for those who are not familiar, right, the momentum-based methods is you are effectively using prior to iterates to figure out where you want to go. And this, so here the term momentum is not coming up well, but this is alpha is the step size. Yk is a linear combination of your previous two iterates, and you are computing the gradient at that point. So the analysis you do is pk minus qk has to be equal to 1. It doesn't show up very nicely, but so we call this general accelerated gradient method, where if I take pk to be 1 plus beta k and qk to be beta k, then basically we get our classical momentum-based version, which is this beta k is called the momentum parameter, time varying momentum here, right? Rather than doing a constant momentum. This approach, of course, is very general. If beta k is 0, I go back to gradient descent. If beta k is taken to be k over k plus 3, we go to Nesterov's accelerated gradient method, which gives you the best rates for example, convex functions of 1 over k squared. If I pick beta k to be a constant, then I get to constant momentum. We have proposed, well, not we, there are other groups which had also looked at it for convex functions, a generalization of Nesterov's momentum for k over k plus 3 minus r, for r between 0 and 3. So effectively, as you increase your r, right, you are making your momentum beta k term larger, okay? And they showed the convergence for that. And that is effectively what allows us to think about, trading off momentum versus escape versus convergence. So to do the analysis for this, it's much challenging because if I think of it as a dynamical system, I have two kinds of dynamics that I can look at. I can look at dynamics in n dimensions, which is the forward map that takes my xk to xk plus 1. But this dynamics does not have a very clear closed form expression, okay? A better dynamics to look at is actually lifting the problem to 2n dimensions, where you are then looking at the mapping of xk and xk minus 1 to xk plus 1 and xk. And this map has a precise closed form expression. You can write its Jacobian and you can prove some nice things about it. So based upon our analysis, we actually go back and forth between analyzing accelerated methods in as a dynamical system in n space or nk map, or 2n space or pk map, okay? And the results we prove in 2n, we do it because we couldn't prove them in n dimensions. So for the first result we prove is that the almost sure convergence, non-convergence from strict saddle for accelerated methods. General methods doesn't have to be non-convex functions, doesn't have to be heavy ball. In the following two cases, first of all, we show that if beta k converges to beta, which is less than square root of 1 by 2, then in 2n dynamics, so under the pk linear dynamical system, we converge to a local minima, and almost surely we do not converge if beta k converges to beta, which is smaller than 1. So this covers the Nesterov's method, okay? So if beta k converges to beta, which is less than or equal to 1, then we do not converge almost surely. But the almost sure convergence requires alpha to be strictly less than 1 over L. For equal to 1 over L, things break down, okay? And we couldn't pinpoint that 1 over L part because this requires actually proving that your pk map is a local diffeomorphism, and things started breaking down when we put alpha equal to 1 over L. But you can get arbitrarily close to 1 over L. So this is the first result that shows the general accelerated methods with time varying momentum, including nag, for general non-convex functions almost surely do not converge to strict saddle points, but in 2n dimensions, okay? So we are trying to actually come up with an example where perhaps like is 2n dimensional result not enough for n dimensions? And that is actually one of the questions that one of the referees asked. So we hope to have a revision and answer and for that. Okay. Now, the challenge here is analysis is more challenging, and I want to at least point that out, right? We can start, so exit time, the question of exit time, again, we have to do it in 2n dimensions. We can't do it in n dimensions. Why we can't do it in n dimensions? Because that n dimensional forward map doesn't have a good, neat expression, a closed form expression. And so we can't compute, for example, Jacobian and talk about that. The other issue about exit time in 2n dimensions, we have the same stuff, right? We are sitting at x star, x star. We can prove that in 2n, the strict saddle here coincides with the strict saddle in n dimensions. But the problem is that we know accelerated methods are not monotonic in Euclidean distance. So I can't use the 2 norm here, right? And so what should be my metric over here? What should be my metric over here? That is the key, because I need a good Lyapunov function in which things stay monotonic. And I'm still after the same thing. I want condition under which I have linear time escape. And to do that, basically, we have to analyze PK map and its limiting behavior. We have a theorem that talks about it. I'm sorry, I'm going to rush because of time. I'll get to the gist. This is not that important, but the fundamental thing is we have to analyze properties of PK. One of the key things is that the Jacobian of this dynamics, right, converges uniformly on compact sets to a limiting Jacobian. And the limiting Jacobian has the same form as you would expect, that take the pk's to p and the qk's to k. So it has the form. And so we can break down, since the Jacobian has this form, it's of course non-symmetric. So I can do its eigen decomposition. If the limiting Jacobian is a defective matrix, we can still do it, but right now assume that it's not defective. You have eigen decomposition. And so what we do is, first of all, the question of stable, unstable, and stuff like that corresponds to the eigenvalues of this limiting Jacobian. Okay? So the stable subspace corresponds to the eigenvalues of this limiting Jacobian, which are less than 1. Here I'm going to include the center subspace, which is the absolute value is 1. And the unstable is, which gives me repulsive dynamics. So Zi, the absolute value is greater than 1. Okay. But the name of the game is still the same. I want to look at the projection onto that, but I have to first define the Z metric, the G metric, the metric. So that is simply given by transformation with respect to my eigenvalue. So V inverse and V. So using the V inverse, right? I can come up, and in this metric, it turns out that, we can have monotonicity of the trajectories. Okay. And the end result is, and there are some limitations. This result is, this is a sufficient condition result. This only holds if either all of my unstable eigenvalues are equal, or I have only one unstable eigenvalue. The other requirement is that in this case, unlike the gradient descent, you better have arrived at the saddle after a few iterations. You can't immediately start there. If you immediately start there, we can say a few things that is in the paper, but not exactly this result. So, and why is the reason? Because if you started right from there, you haven't imparted enough momentum into the problem. Okay, so there are a few distinct differences, but this sufficient condition, if you compare, this is your alignment, your angle can be epsilon log epsilon inverse, which is better than the gradient descent. So the region, the alignment with the, or non-alignment with the stable one here is more relaxed than the gradient descent. We have a lot of other results that basically we can talk about, but one of the key results is that higher momentum, right? So we looked at this generalization of Nestor's accelerated gradient using the momentum of k over k plus 3 minus r. Increasing r makes you higher momentum. What it shows is that actually higher momentum leads to faster escape, but at the expense of slower convergence to local minimum. So there is this trade-off between the two things, okay? Which makes sense that higher momentum is not letting you get pulled into into your region of attraction, and that same reason you won't actually do it at a local minimum, okay? So we can do some experiments, and here I'll just try to just show one result. This is for the case, again, beta k plus 3 minus r equal to 0 is Nestrov's method. And this is, these are the projection values, all the parameters are above. And what you see is that you start from a distance, right? We are running it, you get closer, you get pulled more towards the saddle first, but then you start escaping. Okay, so one of the things is you start escaping faster, but you also get pulled a little bit closer to saddle with higher momentum first. So this is here, the red is, this is Nestrov. Okay, so you can see that it doesn't get pulled that much to the saddle, but it also escapes much later, whereas over here, in about half the iterations, it has started escaping and escapes much faster. There are a number of, for accelerated method, again, the paper has a lot of unanswered questions, as I just gave you sufficient condition. We don't have a good method to, for example, perturb, right? If checking the condition. The sufficient condition I gave you, we have necessary condition, but the sufficient condition requires all the eigenvalues are the same, or absolute values, not the absolute values of all of your complex eigenvalues with the unstable subspace either are the same, or you only have one-dimensional unstable subspace. Otherwise, the sufficient condition doesn't hold. So a lot of interesting open questions, and I'll leave you with this, that, if you want to analyze things, asking questions where we are, rather than simply saying, oh, am I at a local minima, right? Then the traditional tools that we have been using for optimization probably are not the best tools. We have been asking about, do I leave the saddle neighborhood? Am I at a flatter region of the saddle? How do I get closer in that direction? In that case, the classical tools of just let the gradient norm go to 0, do the telescoping sum, descent lemma, and all those tools, they are not going to give you that. You can do approximation as ODEs, but that is alpha going to 0. So that's not good enough. So we need new set of tools. I don't think that we have built the best tools, but hopefully that will be an invitation for people to look deeper into these questions. So I'll end here. Thank you.
More questions for Wendy? Yes, quickly. So, like along the lines of Solar's question, so you didn't do a random initialization because you're specifically trying to see how does gradient descent behave when it's close to this little sliver of space. So do you guys have an understanding for, even for some specific interesting functions, that like how big is that space, and so meaning like, and then I guess the equivalently, if you get farther and farther, does gradient descent do better? But your method that I don't remember the acronym, does it also sort of meet the same performance?
Yeah, so there are two part questions. So let me answer the first part. We have not specialized our problem. So for example, as we talked about, there's a whole set of papers that have looked at saddle escape with a specific functional geometry, right? We have not looked at that, and in that it would be interesting to see how can you map it to those things. But already their results there are pretty good. So it's not clear if you will get something, but maybe there is some middle ground. Random initialization, this basically the key thing over here is, right, that of course in a practical method, you are not going to initialize on the boundary of the strict saddle. You started somewhere. And the main thing over there is, right, that when you should do that randomization step, okay? So the theory here effectively tells you, oh, check this condition and then see if you need to do this randomization step. Otherwise, you are needlessly just perturbing your system. So, but in general, right, what this is since the sliver of that area is just, from, if you just do Lebesgue measure, assign Lebesgue measure to all the regions, it's going to be so small that if you did randomization, you are gonna knock yourself out of that. So randomization is good, but the thing is, we never initialize. I mean, for theory, it is good to say or assume you randomly initialize, but in reality, you are gonna take a path to get, and once you get there, you need to ask yourself, when do I do? Perturbed GD keeps on saying, oh, add noise, continuous add noise. It's not clear if that's the best thing. And also, that can throw you off when you get closer to a local minimum. You don't want to do that, okay? So that's the first part of your question. The second part is CCRGD. I agree, it's not as fancy as grouse or, yeah, so for that, basically, once if your norm is not small, if your gradient norm is not small, you're not in a local neighborhood of a stationary point, then it's just gradient descent. So so effectively what we are calling CCRG, it's really about a check and changing things. So it's gradient descent all the way effectively.
Any last question? Yeah.
I have one question, but I can save that for our meeting.
Sure.
So yes, okay, so I do agree with, and by the way, thank you for raising topic. Very, very interesting. But so when you say adding perturbation at every, let's say you have a small gradient norm. When you have a small gradient norm, you have perturbation, right? This seems a little bit inefficient, but if you look at, for example, you mentioned Chi-Jin's paper, right? They analyze that algorithm and they show that the convergence rate is essentially the same as gradient descent when you converge the first order, right? So it's 1/epsilon squared.
Yes.
So I'm not entirely convinced why adding perturbation is in fact could be inefficient.
So I mean, part of the thing is, first of all, there is still a high probability argument there,
Yes,
right?
yes.
Second thing is, I'm not trying to say perturbed GD is somehow a bad idea. I'm just saying that actually this analysis also tells you that, do you really need to add noise every point or not, right? Secondly, when we all know that rate is one thing, and technically you could perhaps say, well, all of these are effectively look like similar rates, right? So rate is one thing, and constants in front of the rates is another thing. So now that doesn't mean we have done a very deep study of this and explored, because again, my goal is not to sort of downplay perturbed GD per se. My goal was really to understand the foundational ways in which gradient descent trajectories are working. But yeah, one could do more analysis if I was really interested in, oh, we beat them. That's not my goal. But the lesson here could be like, well, why add noise constantly every time? Because there is still a non-zero probability that you could be thrown off, right? And one could look at examples, and maybe I should assign that to a student to actually answer more deeply your question.
Thank you.
Yeah,
Okay,
thank you.
Same one here again.
Thank you. Thank you so much for the wonderful question. I appreciate that.
Yeah, thanks. Right, so someone actually signed up to take you to.
Yeah, thank you so much.
Yeah, thanks for the great talk.
Yeah, you guys know each other?
No,
Okay,
it's the
so
first time.
he was.
Yes, we'll meet later in the day.
Yeah,
But I've
so-
read your papers. And
Okay.
we have some work that is kind of related. We
Okay,
can discuss.
appreciate that.
I really enjoyed your talk.
Thank you. Appreciate it.
Large.
Well, that's really.
Like some-
You can come.
Okay.
It's the 40.
Yeah.
I don't wanna, my students are traveling. I could even stop by earlier because, we'll discuss.
Thank you. Appreciate the attendance and the question.
Thanks.
Ah.